So the last couple of things we did were to see what happens when you switch the rows of the determinant, and also when you multiply a row by some number, right? And those things you probably recognize, right? Switching rows, multiplying a row by a number, those are both elementary row operations, right? So what we're seeing is the interaction of the determinant with the elementary row operations. And so today you can guess what's going to happen. We're going to see what happens to the determinant when you act on a matrix with the last elementary row operation. That is, when you multiply one row, when you add a multiple of one row to another row. Okay? So that is right. That's where we are. Right. So so just recall. We showed you have an n by n matrix, right? If A prime is obtained from A by switching two rows, then the determinant of A prime is minus the determinant of A, right? If A prime is obtained from A by multiplying a row by alpha, then the determinant of the new matrix is alpha times the determinant of the old matrix, right? And as you can expect, what we're going to say today is if you have a matrix B, which is obtained from A by adding a multiple of one row, adding a multiple of one row onto another, then the determinant of B is going to be, well, what do you think it's going to be? Maybe some of you know the punchline. What happens to the determinant if you multiply one row and then add it onto another row? Anybody know the answer? Kathy?
Is it unchanged or?
Nothing. Yeah. Nothing happens. So the determinant doesn't change at all. So that's the joke. Okay. So this is the most complicated of the three. You remember? Let's remember how we proved. This one was easy, right? Multiplying a row by alpha caused the determinant to be multiplied by alpha, right? You just took the cofactor expansion down that row, right? Right. This one, do you remember how we did it? We switched two rows, and then to say something about the determinant of the resulting matrix, what did we do? We took the cofactor expansion. We took the cofactor expansion along. Did I remember?
A row that wasn't one of the.
A row that wasn't one of those two rows, right? You took the cofactor expansion down one of the rows that wasn't one of the rows that you switched, right? And then you noticed that, oh look, the cofactor expansion involves the determinants of minor matrices, which are the same as the minor matrices of the original matrices, but with two rows switched, right? And then we use the inductive hypothesis, right? By induction, we can assume that the determinants of those guys were negative the determinants of the original guys. And so that means that the determinant of the switch guy is, do you guys remember this? Should we do it again? I don't know. No, let's not do it again. Okay, we're not going to do it again. In any case, we did it by induction, right? We did it by induction. We said, suppose you can assume it for n minus 1 by n minus 1 guys, and then you take the cofactor expansion down one of the rows that is not one of your switched rows, and notice that the minor matrices are smaller matrices with switched rows, and so their determinants are negative, those of the original. And that's how you get your -1. Okay. That's how the negative number comes out. Okay, So, okay. So, we're going to do something similar right now, something along the same lines, okay? But instead, we're going to switch rows. Well, not exactly. We're going to we're going to make a copy of a row, and then we're going to expand down one of the copied rows. Okay. So let me make this clear. So it's going to be this lemma, and I'm going to call it this is not what the book calls it, but this is how I'm going to call it, the wrong cofactor lemma. Okay. So you have an n by n matrix, and then AI1, AJ1 plus AI2, AJ2 plus AIN, capital AJN equals, well, if I and j are the same, then this is just a cofactor expansion down a row, right? If I and j are the same, then what we're doing is taking the cofactor expansion of the determinant down a row. Like we get AI1, capital AI1, AI2, capital AI2, blah, blah, blah. If I and j are equal, then this is just, so what is this? If I and j are equal, then what's this? It's just the determinant. Yeah? It's just the determinant of A if I equals j. And here's the funny thing that happens. If I is not equal to j, so you use the cofactors from a different row. Okay. You use one particular row's constants, but you use the cofactors from a different row. If that happens, then you end up with 0. Okay. Okay. So in other words, if you want to think of this in terms of orthogonality, right? If I is not equal to j, then the vector AI1, AI2, AIN is perpendicular to the vector of cofactors, AJ1, AJ2, AJN. Right? Because you see that this thing here is the, what is this? It's a dot product, right? It's the dot product of this thing against that thing, right? So if it's equal to 0, that means that they're perpendicular to each other. Okay. So that's what the wrong cofactor lemma says, that if you take the right cofactors, then you get the cofactor expansion. If you take the wrong cofactors, well, in fact, those things are perpendicular. Okay, and you get 0. Okay, and that will be the key to proving our result about the last elementary row operation. Okay. Okay. So here's the proof. So first off, we've already noted that if I equals j, we get the determinant of A. Right? This was the useful theorem. Right? You can take the cofactor expansion down any row. Right? This is the useful theorem. Okay. So now we're going to do something funny. Consider the matrix C, which looks like this. A11, A12, A1n, AI1, AI2, AIN, AI1, AI2, AIN, N1, N2, ANN. Okay, where this is the ith row, and this is the jth row. The ith row of C and the jth row of C. So it's a copy of the matrix A. but the jth row has been changed to a copy of A's ith row. Okay, so it's the jth and ith rows of C are the same. They're both A's, the matrix A's ith row. Okay. Okay. Does anyone see how to get to the end? Why does considering this matrix give us that if you take AI1 against capital AJ1, blah, 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 you get 0? How do we get a 0? Just think about it for 1 minute. Walk around. Leave the door open so you become more hot. Talk to each other, maybe?
So we're just supposed to figure this out as a unit. Does anyone have an idea what's going on? Just spitball.
Yeah, I think it's because since the two rows are the same, if you're taking the bottom one, you're doing the same. So then if you get the determinant, you're also getting the 0. So the determinant is 0.
Okay, Elena, go ahead.
I think it's because those two rows are the same.
Yes, so the determinant of C is
well, it's 0.
0, and it's also, we can also express the determinant of C as you say, I think you were just saying it as
as the cofactor expansion, and then
down the what row?
Down the ith row.
The jth row, actually.
Okay.
We'll go down the jth row. So let's take the cofactor expansion down the jth row. We get AI1 times CJ1, right? This is the jth entry. This is the J1 entry. Plus AI2 CJ2. Right, maybe I should write it, it's going to be CJ1, capital CJ1, plus CJ2, capital CJ2, plus CJN, capital CJN, right? CJ1 is, of course, AI1. AI1, these guys are all AI, right? Right? CJ1 is what? Capital CJ1 is the same thing as capital A J1, right? Because we're taking the cofactor, right? We're taking the CJ1 cofactor, right? Which means that you take -1 to the something plus something, and then you take the determinant of the minor matrix, right? But if we cross off the jth row, C and A are the same matrix, right? C and A are identical, except that the jth row of C is a copy of the ith row, right? So if we look at the minor matrices, well, right, if we look at the determinant of minor matrix of C here, right, it's the same thing as the determinant of minor matrix of A. You're looking confused. Are you confused?
I would say I am.
Good, thank you, thank you, thank you. Right, so, let me write it again. Okay, so, right, so we start off with this matrix C. We start off with the matrix A, right? Then we make this thing C, obtain it by taking exactly A, and then taking the ith row of A, and copy and paste it on top of the jth row, the original jth row. Okay, so this matrix C looks exactly like A except in the jth row. Okay, so now let's look at the determinant of C. Well, the determinant of C is going to be, we'll expand it, so take the cofactor expansion down the jth row of C, right? We end up with, AI1 times the cofactor CJ1, excuse me, CJ1, plus AI2 CJ2 plus AIN CJN. Okay. Is everyone okay with that? Everyone okay with that statement? Henry.
Wait, so you have so the AI1 is just because you're pulling the determinant off of the jth row, right?
Yeah, yeah. Right.
And then, but then the C, where do you get the
well, I mean,
uppercase CJ1?
Right, really, I should write this, right? CJ1, CJ2, CJN. Right? This is the cofactor down the jth row. You take the CJI guy times the CJI cofactor, CJ1 cofactor, CJ2 guy times the CJ2 cofactor, et cetera, et cetera. That's the cofactor. That is the cofactor expansion.
Okay.
Okay. But now let's notice that CJ1 is AI1, right? Because of our cut and paste that we did earlier. Right. So this is that. This is that. This is that.
Okay.
Right? Just because of the cut and paste, right? So we get this. Right? And then we observe that CJ1 is the same thing as AJ1. The cofactors of C down the jth row are the same as the cofactors of A down the jth row. Right? Right? Is that obvious? That should be obvious. Maybe it's not. So right, remember what the cofactor is. I think maybe you've forgotten what the cofactor is. What's a cofactor? What's a cofactor? Well, that's the trouble. People have forgotten what the cofactor is. What's a cofactor? Anybody know what the cofactor is? When you take the determinant of the minor matrix you get by crossing off. Yeah. And you also have this number, -1 to the sum of the indices. Okay. Right, so you have -1 to the j plus 1 times the minor matrix of A that you get by crossing off the jth row and the first column. Right? Over here, what do we get? We get -1 to the j plus 1 times the minor matrix, now this is a bit misleading, maybe I'll put a pine here, times the determinant of the minor matrix you get by crossing off the jth row and first column of C. Right? Well, if I take off the jth row and the first column of C, the matrix I get is identical to that I get from A, right? Because the only difference between A and C is the jth row. I just crossed off the jth row, right? So the determinant of C's minor matrix is going to be the same as the determinant of A's minor matrix, right? And so these guys are equal. So is that clear? Is that clear? Anyone not get that? Okay, great. Okay, so then we write it. We see that we can write it like this. Oops. Okay. So we see that the determinant of C is this thing here. but C has two identical rows in it, and so we know that the determinant of C is 0. Right? And that tells us that if you take the cofactor expansion of A, but use the wrong cofactors, use the cofactors from the wrong row, then you end up with 0. Okay, that's the proof of the wrong cofactor theorem. Ask questions. I think it's not completely. People are still look a little confused. Ask questions, please. Teresa.
Can you clarify how you got to 0? Because I followed you all the way to when you said.
Yeah. So right.
Because
The
I noticed
determinant.
that correlated.
Okay. So the determinant of C is this thing. You're okay with that?
Yeah.
Okay. And then you say, but the determinant of C is 0 because
There's 2.
C has two identical rows.
Okay.
Right?
Yes.
So this is 0.
Okay.
Right? So that expression we were hoping was 0. Right? Is 0. Right? Yeah, Mia.
I'm still not getting the jump. Like, why are we saying the determinant of C equals 0?
Well, the determinant of C we expressed as this thing, right? Right? Are you okay with that part?
Yeah.
Okay, great. And then we look at C again, and we notice that C has two identical rows, right? The ith row and the jth row are completely the same,
Mm-hmm.
right? And if you have a matrix with two identical rows, then its determinant is 0.
Isn't that what we're trying to prove?
No,
Oh.
no. No, we already knew that, right?
Oh, okay.
We already knew that what we're rather trying to prove is this fact, that if you take a cofactor expansion, but use the wrong row's cofactors, you end up with 0. That's a completely different statement from
Okay, yeah.
from saying the determinant of a matrix with two identical rows is 0. That's a much more complicated statement. Yes, Andrew.
So if you go down the first row, is the determinant still 0, or is it only if we do
Yes.
the cofactor expansion down the jth row?
It doesn't matter, right? The determinant is going to be the same no matter what row you take it down, right? This matrix has two identical rows, and so the determinant is 0 no matter what row you take it down. It's just that if we took the expansion down the first row, it wouldn't give us the information that we're looking for. Okay, we get the information we're looking for by taking the expansion down the jth row, which is a copy of the ith row. Okay, so don't worry if you don't understand it immediately. Go home and think about it. That's fine. Like I said, I understood myself only maybe 5% of what my professor said, and then figured it out later. So don't worry. This is a little bit tricky, but you'll once you see it, you say, oh, okay, of course. Okay. So, right. So what we've shown is that, right. We've shown this lemma that if A is an n by n matrix, then if you take the cofactor expansion, you end up with the determinant if I equals j, and you end up with 0 if I is not equal to j. Okay, so now let's use this thing to show that that the third elementary row operation does nothing to the derivative. Okay, so let's give the proof of the third fact that we listed this early at the beginning of class. Okay, so let's say that B, the matrix B, is the matrix A, but with the kth row turned into RK plus CRI. Okay, so you take the matrix A, And then you take the kth row and add on k copies of the ith row onto that. Okay? And you end up with this guy, B. Okay? In other words, using the book's notation, the kth row of B is C times the ith row of A plus the kth row of K. Right? You take the kth row and you add on C copies of the ith, right? And you get this new guy. Okay. So obviously, if we look at the cofactor bkj, right? That's going to be the same as akj for j equals 1 in n. Right. If we, again, this cofactor involves crossing off the kth row. Right? If we cross off the kth row, then B and A are identical. And B and K are identical, right? So these cofactors are the same, right? Since the Kj minor matrices of B and A are the same. Right? Okay. So, what do you think we're going to do? What do you think we're going to do? How are we going to calculate the determinant of B? What move do we make next? Here's sort of the big clue. The cofactors are the same down the kth row. So
Do cofactor expansion down the key.
do cofactor expansion down the kth row. So expand determinant of B down the kth row. Right. You end up with BK1, capital BK1, BK2, capital BK2, BKN, capital BKN. Right. The determinant of B is going to be that. Right. Well, what is BK1? Or maybe easier, what's capital BK1? Well, that's AK1, right? All the cofactors are the same down this row, so we can replace these guys with their corresponding cofactors from A. Okay. Now, also almost even easier question: what's BK1? BK1 is the k1th entry of B. Right? B we got from A by adding on C copies of the ith row onto the k. So what is it? BK1 is C A I
CAI1.
Thank you. CAI1 plus A K
1.
1. Thank you. What's with you guys today? Is it too hot in here? No. You're sleepy. You're in pain. You're angry. You're sad. I don't understand people, Chrissy. I don't. Okay, right, because you've added on k copies of the ith row onto the kth row, right? So, I'm sorry, C copies of the ith row onto the kth row, right? So this is going to be CA1 plus AK AK1, and so on and so forth, right? So you end up with, right? You end up with CAI1 plus AK1, capital A K1 plus CAI2 plus AK2, capital AK2 plus CAIN plus AKN, capital AKN. Right? Maybe you guys see the joke at this point. Maybe you guys see the punchline right now. Okay. What happens? I'll let everybody think for a minute. What happens, right? You get C times AI1, AK1, AI2, capital AK2, plus AIN, capital AKN, plus AK1, capital AK1, plus AK2, capital AK2, plus AKN, capital AKN. In other words, you get, what's this?
So that's 0.
0 plus the determinant of A. Yeah, Andrew.
Why is it 0?
Why is it 0? Anand, why is it 0?
Because you are expanding along the ith row with the cofactor of the kth row.
Yeah, by the wrong cofactor limit. You see, this is exactly, you're doing a cofactor expansion, but with the wrong cofactors, which we just saw as 0. And here we have expansion, the cofactor expansion with the right factors and the right cofactors. Okay. Any questions?
Wait, so
Yeah, Teresa.
both turn to 0 because of the code?
No, only this one turns to 0.
Oh, okay, and then you get the determinant of A.
This one is the determinant. Yeah.
Okay, but the determinant of A is not 0.
No, I mean it could be, but
Okay.
it's the determinant of A. So what do we see? That the determinant of B equals the determinant of A. Okay. Any questions? Should I let you all rest or something? Do you need a rest? Do you need to stand up and stretch? Do you need to go and run around? Dance? Sing? I don't know. Take a nap. Okay. 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 So there's another way of. So what we just noted is how the elementary row operations are affected by the affect the determinant, right? There's another way of phrasing this. So rephrase it. So first notice that if E is an elementary matrix, then the determinant of E is going to be -1 if E affects a switch. It's going to be alpha if E scales a row by alpha. and it's going to be 1 if E adds a multiple of one row to another. Okay, so you can see that, just check it yourself. Okay, I'll ask you to take a look. It's easy to see that this is true. Okay. So so our 3 results could be summarized as this. Given any elementary matrix E, the determinant of EA is the same thing as the determinant of E times the determinant of A. Because our result says that if you have a matrix and you switch 2 rows, then the determinant of that is going to be -1 times the original determinant, right? Well, that's what if the switch matrix has a -1 determinant, so that's exactly what that says. Our result also says that if you have a matrix and you apply a scaling matrix to it, and you scale 1 row by alpha, well, you're going to get the determinant of A times alpha, right? Well, that's this, right? And we just said that if you have a matrix and then you add a multiple of 1 row onto it, then the determinant gets multiplied by nothing, by 1. Right? The determinant doesn't change, right? So this statement here encompasses the 3 things that we said.
Can you repeat what you said for -1?
Yeah. So if you have a matrix and you switch the rows, right? That is, you switch 2 rows. You could say that as I have a matrix and I apply an elementary row switching matrix to it, right? What we saw was that the determinant should be -1 times the original determinant, right? And that's what we say here, right? We get the original determinant times -1, right? Because the determinant of the switch matrix is -1.
Oh.
Okay. So this includes what we're saying. Okay. So So this gives us the following corollary. A is invertible if and only if the determinant is non-zero. That is, the determinant gives you another way of telling whether a matrix is invertible or not. Okay. So let me sort of state something down here. So in fact, if we have this theorem here, we have this observation here that if you have an elementary matrix, the determinant of E times A is the determinant of E times the determinant of A. In fact, there is sort of a bigger theorem. The determinant of AB is the determinant of A and the determinant of B for any square matrices. Okay, they need not be invertible matrices. They need not be elementary matrices. Okay, that will follow from that follows almost immediately from this. So I'm going to ask you to read this yourself. Read yourself. But right now, let's go back to this thing. Okay, so here's the proof of it. Let U be the reduced row echelon form of A. Okay. Let it be the reduced row echelon form of A. Okay. Okay. So if A is invertible, then what's U? What's U, right? If you have if A is an invertible matrix, you reduce it down to its reduced row echelon form, and you get what?
Non-zero? Zero.
I, right? I, right? You get I. One gets I. Right? Then U is I. Right? So, the determinant of U is 1, right? Right? Because it's the identity matrix. The determinant of the identity matrix is 1, right? But that tells you that the determinant of A is what? Could the determinant of A be 0? No. Right? If the determinant of A were 0, that would mean that, you know, the determinant of this product here would be the determinant of this guy times this guy times this guy times this guy times 0, which would all be 0. Right? From the previous fact, right? The determinant of an elementary matrix times A is the determinant of E times the determinant of A. Right? So here we see that the determinant of U is the determinant of EK times the determinant of EK minus 1 times the determinant of E1 times the determinant of A. Right? And all these guys are non-zero. Right? Right? It's either -1, 1, or alpha, where alpha is non-zero. Right? Okay. So we see that the determinant of A is non-zero. Okay. Now, is that first part clear? If A is invertible, then the determinant of A is non-zero. If A is invertible, then U is equal to I. The determinant of U is 1. Determinant of A is non-zero. And if A is non-invertible, then the determinant of U is, well, what happens to the row echelon form? If it's non-invertible, then you end up with, what happens to the row echelon form? You end up with zeros on the bottom row, right? And so the determinant of the reduced row echelon form is going to be 0, right? But that forces the determinant of A to be 0. Okay, so invertible makes it the determinant non-zero. Non-invertible makes the determinant 0. In other words, invertibility is equivalent to the determinant being non-zero. So we've proven both directions. Right? Invertible implies that, and right, if the determinant is non-zero, that means that the matrix is invertible. Just to make the logic clear, right? In this first part, we show that this implies this, right? If A is invertible, then the determinant is non-zero. Okay. In the second part, we show that if A is non-invertible, then the determinant is 0. Right? If we state that in the contrapositive form, contrapositive statement is that if determinant is non-zero, then A is invertible. Right. I don't know if you're familiar with something called the contrapositive, right? If you have some statement, if you want to show that A implies B, that's equivalent to showing that not B implies not A. These are logically the same statement. This one is called the contrapositive, right? This is the sort of straightforward way. This is called the contrapositive. Okay, so this thing is equivalent to its contrapositive, which is that right? A non-invertible implies the determinant is equal to 0. That's the same thing. That tells us the same thing as if A determinant A is non-zero, then A is invertible. Okay. So that gives us the reverse direction, right? So this part here is the forward direction here, right? And then this thing here is the reverse direction. Okay, and that's how you get the both parts of the proof, right? Both parts of the equivalence. Okay, maybe that's enough for today. See, go home and drink some water.